about these two talks. I probably that's my way of making a disclaimer. You know, probably the organizers, they felt obliged to ask me to speak, and they told me, you know, Anton, maybe you can talk about how you quantize moduli spaces using quadrant orbits. And I think maybe somewhere in the description there is even something like that. And I said, actually I don't. They said, okay. So how you do Hitchin systems? I said, about that I have no clue. They said, okay, good, but you speak of whatever you're doing. Maybe we don't know what it is. Okay. so that's the kind of genesis of those talks. So I'll basically speak about three topics. I don't know how well it fits to the rest of the program. Probably it doesn't. But now, well, there is no way out, right? We are all here. And so the first topic, I will recall the structure of classical geometry of modular flat connections. Of course, some small part of it. And then I'll talk about one of the many deformation quantization schemes, which is called combinatorial quantization. I must say, so at some point I was very much into it, but this was several decades ago. So you will probably see some traces of it in my presentation. And then I will end up with BV structures. So, and all of these things you will see they're in some ways similar. So BV structures, that's something that I was interested in recently. Okay, so to compensate a little bit the deficiency of my preparations, I decided to structure those talks very well. You will see at least there are numbers for everything, hopefully. So the first part about the classical geometry will be called Goldman and Seabot and Fock-Crossley. So many names. What is it about? We start with sigma and oriented to manifold, possibly with boundary. So we can imagine something like this, right? So it's a surface, possibly there are several boundary components. And we associate to it the following vector space, let's say G of sigma. That's a linear span. Topologists typically like to do it over Q, but I do it over R. And here you take homotopy classes of free oriented loops on sigma. Let me try to draw such a loop. For instance, this one. We'll have other pictures for G of sigma very soon. So the classical and very important result about this space is the following theorem. Goldman, which says that the following operation is a well-defined Lie bracket. So let me write it. So we'll have a pair of homotopy classes of those free-oriented loops. And you know, maybe it's slightly confusing, but I will sometimes, by those alphas and betas, mean homotopy classes, but sometimes the representatives. So, of course, if it's confusing, then tell me. So, of course, here it should be homotopy classes. And so let me write the right-hand side. So this will be some over intersection points of alpha and beta. And of course here we do mean concrete representatives, otherwise it does not make much sense. And we assume that we've chosen the representatives such that they have a finite number of transverse intersections. Right? Because again, otherwise the sum may be infinite or whatever. If there is some tangency, it's no good. And here there will be a number which is -1, and I will now explain what it is, times a class of a curve which I call alpha connected with beta at P. And here the picture is as follows. Let me maybe exchange the boards. So here the picture is as follows. Let me draw in two colors. So this will be the alpha curve, and this will be the beta curve. The intersection point is here. And well, it's a bracket of alpha with beta. So alpha is number 1 and beta is number 2. So here the tangent vectors to those two curves which intersect transversally, they form a basis of the tangent space to my two-manifold, and this basis is a positive or negative with respect to the orientation of the two-manifold, and that's the sign. So that's the sign of the basis given by those tangent vectors. And now, what is this curve alpha join beta? So here we can say that there is a singularity at the intersection, right? That those two curves intersect, and since they are oriented, there is a unique resolution of that singularity. So, which looks in this case like that. Note that if you start with two curves, you always get one curve after you resolve one singularity. Okay, now I said theorem, but what does it say, the theorem? So, it's well defined. And easily bracket. Note that it is not entirely obvious that it is well defined. Even before checking whether it satisfies any Jacobi identity, right? Why it may not be necessarily well defined? Because you can change the representatives. So you can, like, those intersection points, they can easily disappear, reappear, and so on. So you need to make sure that actually the right-hand side remains the same, right? And I think if you, of course, maybe many of you are probably much better experts than I am in that stuff, but if you never seen it, I think it's a very interesting exercise. Think how would you do it? In fact, just a hint, you would consider Rademaster moves, right? You need to kind of, what can change? You change representatives and you do Rademaster moves over those pictures. And you need to convince yourself that under those Rademaster moves, nothing can happen to the right-hand side. So then, so they're saying it's a Lie bracket, so it needs to be skew symmetric. That's obvious, because there only the sign changes. And then you need to check the Jacobi identity, and the Jacobi identity, that's another instance with the Rademaster moves. So that's also sort of easy, but these are very instructive exercises. We'll go back to the history of the Goldman bracket perhaps a little bit later. But now maybe I want to make one small remark, and I said everything got to be very much ordered, but now it's not, right? Okay, that's paragraph 1.1. So, a remark. Suppose you take a trivial loop located somewhere on your surface. Then it's easy to see that it belongs to the center of the Lie algebra G of sigma. So why is that? Imagine that you have two curves and one of them is trivial. So imagine you have something like this. But then, since I can choose a representative, I can always move it off. Right? So I can always replace this picture by that picture. And here there are no intersection points. So the sum on the right-hand side is simply trivial. So empty, there is nothing there. In general, there is the following statement. I'm not exactly sure, maybe I should have checked the attribution. So the center of G of sigma is known, and it is spanned by powers of the boundary loops. So, right, your surface has some number of boundary components, and if you have a boundary component, you can organize a loop which loops around that boundary component. It can also loop many times in opposite directions, right? So here, A is in Z, and alpha is a boundary loop. So that's the center of this Lie algebra. And also later on, somehow we're gonna return to this statement. By the way, maybe an interesting thing. I think by now probably right. It looks like some kind of algebraic statement, and I think by now there are probably some relatively involved algebraic proofs. But I think the first proof uses symplectic geometry, and symplectic geometry that we're going to discuss now. Symplectic geometry of moduli spaces of flat connections. So actually, otherwise it's not like very easy to control that object. Okay. So you see that was a story in topology for now. Topology of two surfaces. Now, moduli of flat connections. So, of course, probably everybody here, or kind of maybe almost everybody, know about this stuff, but well, let me just formulate some definition. So now we fix G a Lie group. Maybe to simplify things, possibly connected, and we associate to the surface and to the group a space, which is a space of group homomorphisms from pi 1 to G, modulo the G action, which is an action by equivalences, by simultaneous conjugation. Obviously, this writing is not quite correct, because possibly, depending on the group, maybe you need to choose some of the representations and not to take all representations. In the first approximation, I will ignore this problem for now. So, but of course here there might be a question mark. So maybe more seriously, you have to question what this is. So an important theorem due to a bot, or let's say, I'm not sure they formulated it in that way, but let me interpret it in this way. So again, we assume that G is oriented, and we assume that the Lie algebra of G carries an invariant scalar product. Of course, you would all know about the Killing form in the semi-simple case, but maybe an interesting remark, I don't know whether everybody knows, in principle, many other Lie algebras, for many other groups, they do have invariant scalar products. They would not be Killing, right? It's well known that Killing is non-degenerate only in the semi-simple case. But other scalar products can easily be non-degenerate in non-semi-simple case, just as an information. Think of a billion Lie algebras. They all have invariant non-degenerate products, many of them. They are not at all Killing, but... all right, so then M sigma G is Poisson. And if there is no boundary, then the Poisson bracket is non-degenerate, and we get a symplectic structure. So it's usually, I guess, in the Thibaut classical paper, it was formulated in this setup, but then it's relatively straightforward to figure out that in general there would be a Poisson structure. So in fact, I started with Goldman, but Goldman, I think that was an attempt to interpret the result of a Thibaut, and we'll now see how it actually works. And what we'll do for the most of the talk, at least until we go to BV, we'll put G to be either GLN or UN. There would be various modifications for other cases, but I think for us it would be cleaner to look at those cases. So in this case, we want to define so-called Goldman map. So that's the map, let me call it G, from G of sigma to functions on the moduli space. So here again, I'm a bit vague about functions, or what kind of functions. We'll get back to it in some moments from now. And there is a famous and very simple formula for that map. So we have a homotopy class of curves, alpha, or maybe a concrete curve representing that class. And we map it to the so-called Goldman function, G alpha. So G alpha should send points of the moduli space to numbers. And so a point in the moduli space is a class of representations, right? Again, let's say rho is a representation, or maybe a class of representations. So this function sends rho with a trace of what? So I should apply rho to something, and rho is a representation of pi 1. But a curve is not an element of pi 1. Imagine that somewhere here there is a base point, right? So then, in many ways, you can promote your curve into a curve attached to that base point, and that would define for you an element of pi 1. Maybe more technically, a curve is a conjugacy class in pi 1, right? So let's take any representative of that conjugacy class. If you want, I can, whatever, by alpha bar. So that's the conjugacy class, or that's an element in pi 1 representing alpha. There are many of them in general. So there are many representations in the class. There are many representatives of that curve in pi 1, but the function is independent of those choices. That's essentially because all the choices, they lead to conjugating that element by something. And the trace is invariant under conjugation, right? So, okay. So there is this Goldman map, and so there are several ways to state the relation between a Tier-Bot and Goldman. So let me give several, or maybe two statements. So so that's again Goldman. So this map G is a Lie homomorphism under what? So of course on G of sigma side under the Goldman bracket, and on the function side under the Tier-Bot Poisson bracket. Of course, this statement tells you in particular that if you take two Goldman functions and if you take the Tier-Bot bracket, you get again a Goldman function. You might have got something else, but you get a Goldman function which corresponds to the Goldman bracket of your curves. Are you still with me? Maybe I want to state it slightly differently. Let me promote this statement into the following statement. Here I'm only mapping Goldman functions, elements of G of sigma, to Goldman functions. Let me now take possibly linear combinations of products. In other words, elements of the symmetric algebra. Right? I can extend it as an algebra map. Product goes to product. Now, it turns out that if you take a symmetric algebra of a Lie algebra, it's automatically a Poisson algebra. So you have a Poisson, canonically have a Poisson bracket, which is induced by the Lie bracket. Are you comfortable with it? So here you have a Poisson bracket which comes from the Lie bracket. So then basically the same statement says that this is a Poisson map. Right? Before I was saying that somehow I was misusing the Poisson bracket as a Lie bracket on the right hand side. But now this is just a map of Poisson algebras. So this is completely like equivalent restatement. But now one can ask the following question. So this map for different ends what are its properties? Is it whatever, injective, surjective? And here is the theorem, and maybe I'm not 100% sure, like certainly Ettinghoff contributed, like whether there are other attributions. First of all, for any n G is surjective. Here I must say, right, it depends a little bit of what is fun. So this is like maybe it's dense, right? If you take whatever really smooth functions, then you don't get everything from this construction. If you take some kind of polynomial or algebraic functions here, defined by whatever matrix entries, then you get everything. So in particular, note that I told you in maybe not great detail, but at least I gave you an honest definition of the Goldman bracket. I didn't tell you anything about this Atiyah-Bott theorem, right? And that's for two reasons. First of all, probably many of you know, but for those who don't know, this would require some piece, whatever, some really extra piece of activity. But this statement tells you what is this bracket, because since it's surjective, you get everything. Furthermore, so there are two statements. The second statement, we can take intersection over n, let me call for just for this line Gn, the map for a given n, right? So the intersection of kernels of all Gn's is actually 0. So this means that, of course, each Gn separately cannot be injective. But if you take all of them, which means that you're looking at the image for all sizes of matrices, so then there is no joint kernel. You would always this means that by looking at moduli spaces for all different n's, you can make a judgment on what happens in this Goldman-Lie algebra. So basically, to some extent, right, these are two languages, geometric language and topological language, which are in some approximation describing the same thing. Okay. So now I still want to talk about the other two names, like 4-cross-Lie, and that's essentially because of the following. So these are all very beautiful pictures, very nice, very conceptual. That's not going to be those pictures that we're going to use in the rest of the talks. And now maybe, okay, these are 2 hours, right? So I can also show you a little bit of more real stuff. And so this story, at least for me, does not allow me enough technology to work with it. So I'll now show you a kind of breakthrough of 4-cross-Lie, who gave their interpretation of the Atiyah-Bott bracket, which allows really to work with it. And we're going to see why. So, so 4-cross-Lie brackets. Maybe conceptually, the main difficulty, maybe I want to rewrite it again. So the main difficulty is as follows. Recall the definition of M sigma G. So this is Hom by 1 sigma G divided by G. And the problem is this division by G. So this means that we should take functions on home pi g, and then consider only invariant functions. And instead, you want to work with all elements of home pi g, especially in the case when there is boundary, pi is a free group. This means that home pi g is just a number of copies of g. So we want to capitalize on that. And so that's the construction. So Fock and Drossley define brackets on home pi g directly, which would then descend to the moduli space. So now we assume that the boundary is non-empty. And here I'm not doing exactly the same thing as Fock and Drossley. So gamma inside sigma will be a ribbon graph. And I will now draw such a ribbon graph. So let me choose an example of a surface. So this will be a sphere with 3 holes. And so here I will choose a base point. And here will be my ribbon graph. So ribbon means that I need to have some flat ribbons which wind around my surface. So now there will be several conditions. I can have several vertices in the graph. Here there is only one vertex, but I can have several vertices in the graph, but they should all be on the boundary. And you see, the surface actually now retracts to that graph. If I want, I can retract the surface to the graph. So in fact, Fock and Drossley, they consider more general graphs, but maybe for our purposes that will be more convenient to restrict a little bit. Now, recall that my Lie algebra G carries an invariant scalar product, and this means that in the tensor product of 2 copies there is a canonical element. Right? If you have a scalar product, there will be a canonical element. Something like the sum of EI tensor EI, where these are 2 dual bases with respect to your scalar product. Now, Fock and Drossley make a further choice. So R will be a solution of the classical Yang-Baxter equation such that its symmetric part, right, you can always flip, should be exactly equal to T. Now, these words, do they say something to everybody or not really? Maybe I write it down. So this is, we don't want to dive into it, but this is some kind of nonlinear algebraic equation. So we consider a product of 3 copies of the enveloping algebra of G. And here we consider elements R12, which is R tensor 1, R23, which is 1 tensor R, and R13. May I leave it to your imagination how R13 looks like? You would need to put 1 in the middle component. And then the first component of R here, and the second component of R there. Now the equation looks as follows. So I think one of maybe doesn't, if you've never seen it, doesn't look very convincing. So later on, maybe in the second hour, we'll see the quantum. So this is a classical Yang-Baxter equation. We're going to see quantum Yang-Baxter equation, and the quantum Yang-Baxter equation perhaps would be telling you, would be more like appealing. And this is the infinitesimal version of the quantum Yang-Baxter equation. Also, we need this to ensure the Jacobi identity of the four-Crossley bracket that I'm about to describe.
Sorry, would you explain why you assume that the boundary is not zero?
Sorry? Oh, because I want to put the base point on the boundary. That's one consideration. Another one, because I want phi1 to be free. So that's maybe that's even more.
But for your quantization, you don't need it necessarily.
No. But yeah, we're going to discuss it. But all right. So now we're going to consider the space of graph connections. And by definition, this will be G to the power this set of edges. In particular, if you have only one vertex, then it is automatically isomorphic to form phi1G if the gamma is a single vertex, right? So that's a very easy space, right? It's a product of some copies of our group. Now, on that space, Fogg and Drossley write a bivector. So how does this bivector look like? In case we have several vertices, it's a sum over vertices. Now, at each vertex, right, the vertex is sitting on the boundary, and the surface is oriented. This means that there is a linear order on the set of edges. Maybe for those people who have seen the four-Crossley construction before, right, they don't necessarily place vertices on the boundary. They may be placing them on the middle, but then there is only cyclic order, and one needs to choose the linear order. This goes under the name of eyelashes that you add somewhere, but like I don't want to dive into it. So if the vertex is on the boundary, then there is a linear order, like 1, 2, 3, 4. And here there is a sum over pairs. Right now, these are the numbers.
Wait, this is order on what? I'm sorry.
On the star of the vertex, which means on the set of half edges.
Half edges, okay.
Entering on the set of
terms
half
of edges.
So these are half edges at V. And here, let me write Rij and explain what it is. So let me recall that R is in the tensor product of two copies of G. Now, each copy of the group carries two G actions by left and right translations. Now, so this G to the power E gamma, right? To each edge correspond an element of the group. And each edge has two half edges, which may be at the same or at different vertices. So if we orient them, then we'll know which one is left and which one is right. We just need to make a convention. For instance, the beginning is left, the end is right, or whatever, the other way around. So with this convention, we actually know that each of those elements of G corresponds to a vector field on that space. So, and we want a bivector, right? A product of two vector fields. So it's bivector on G to the power E gamma. So again, to each edge corresponds an element of a group. So an element of a group carries two actions on the left and on the right. And this means when you write here a pair of half edges, you know how to act on which elements of the group. So this is, it's both simple and complicated formula, right? So, right, there are many choices, but then the writing is very compact. So why do we speak about it? How is it related to the rest of the story? So let me state the theorem of Fock-Drosley. So this, maybe several things. So this gadget is a Poisson bracket, right? So that's the first statement, and that's essentially because we have this classical Yang-Baxter equation.
Is it equivalent to classical Yang-Baxter equation?
Maybe not. Okay, that I would need to think about, but maybe not. But certainly the classical Yang-Baxter equation implies, that's for sure. Like, I would need to recall equivalent. Okay, let's say I don't vouch for that for now.
Jacobian identity is a kind of quadratic relation. This is also a quadratic relation. So
sure, but it's not true that all quadratic relations are equivalent.
Well, if one of them implies the other, then
there is no theorem like that.
That's true.
Okay, so in any event, pi fr is a Poisson bracket, and second, pi fr restricted to so we can consider functions on the moduli space. These are invariant functions under the G action, right? So restricted to fun and sigma G, which is fun home phi G invariant. So this is equal to the Atiyah-Bott bracket. In particular, it's independent of the choice of R. Perhaps there were many R's, right? R should have the property that I've written here, right? R should have the property that is related to T. And a T abort only depends on the scalar product on the Lie algebra, right? So if you choose some other R which has the same symmetric path, you're still fine. Moreover, maybe a small remark about that. You can do pi of r tilde, where here you would just write Tij instead of Rij. So this gadget is not a Poisson bracket. It has some kind of deviation of the Jacobi identity, so it's called quasi-Poisson bracket. But this property is still true. So you can restrict it to invariant functions. It becomes a Poisson bracket. And this Poisson bracket coincides with the one of a Tn bot.
I guess you need to divide Tij by 2 for this, wouldn't, because
Come on.
you want this,
Okay,
you want T12 plus T21 to be equal to T.
Yeah.
Oh, we have one half over there. I'm sorry. Yes.
No, like division by 2 is tricky. Of course, much less tricky than determining plus or minus signs, right? We can agree on that.
Okay.
But you know, you're right. All my signs and all my 1/2 and many other things are
You're probably right.
very
It's probably
approximate. Not in this formula though. So
So this quasi-Poisson structure is independent of the choices?
So yeah, that's what I was about to say. So this quasi-Poisson structure in that way is independent of the choices. In particular, you can ask what happens if you choose different graphs, right? So it turns out that they are all isomorphic, right? If you choose another graph, so the choice of between two graphs, there would be an isomorphism between those spaces g to the power e gamma. Here I kind of tricked you a little bit. Maybe you can think, suppose we always think of one vertex. So then you can choose different generating systems for pi 1. Like you can now choose another generating system for pi 1, and then you would have another 4-cross Lie bracket. There would be an isomorphism between two representation spaces, and this isomorphism will identify the 4-cross Lie brackets. So I think in some abstract form, maybe this fact that this bracket with T is canonical. I think there was a paper by Massieu and Turaev who made it really precise in terms of so-called double brackets of Vandenberg. But okay, so so much I wanted to tell you about the classical story. I don't know whether you have questions. Now maybe we should decide. So there are like 7 minutes to the break. Should we make a break now and open another chapter just after the break? Chair. I think that you could decide.
It's your choice, of course.
Yeah, I think that's a good idea. That's the end of the story, and then I think it's a bit ridiculous to have another story starting developing for 5 minutes, or maybe I push you in 10 minutes. Yeah, let's do the break, and then we do whatever we can afterwards.
Okay, we start promptly after the break. Okay.
Break until when?
That's a good question. I think it's till
But we can maybe advance a little bit.
Yeah, sure, absolutely.
Yeah,
Yeah.
10 to 6?
Yes.
Yes.
Could you comment again on the regularity of the
Regularity
At some point.
only functions. I think we can safely, let's safely think that these functions, right, we are speaking mostly about whatever GLN, UN, that these are polynomial functions of, say, basic representation or of any finite dimensional representation. So that would already like give you lots of stuff. Mhm. Yeah.
Maybe add a word on the orbits under the group action.
Wait.
When you define-
Orbits, where of which one?
When you define the moduli of flat connections,
Yeah.
you said it's not going too much about.
Yeah.
Could you still?
No, but now now we are saying that these are just let's say I suggest we don't care about geometry. We are just saying that we look at invariant functions. So you have functions. Let's say these are GLN. You have some number of matrices. So these are polynomial functions of those matrices, and you are looking at some action, which is whatever conjugation, multiplication, and you're looking at invariant functions. So the classical invariant theory basically tells you what they are. You need to contract indices by Einstein summation everywhere, and that's how you do it.
By the way, if you try to answer such a question and consider the sphere with three functions, so isn't it true that the Poisson bracket is precisely R12 plus R13 plus R23, and if you compute Schouten bracket of it with itself, it will give precisely this Young Baxter, where each R is kind of a joint vector field on each of three groups.
Yeah, probably. Oh, you mean that it should show us that it's. No, but wait. Like sphere with three punctures, right? Right. For instance, that's the picture. Now you have 4 half edges.
If you do it differently, if you choose two points and draw three lines.
Okay.
So it looks that Poisson bracket is a difference of left vector fields and right vector fields, and it's precisely R12, R13,
On each side.
Yes.
On each side. But maybe there is a right-hand side which would be invariant under the triple conjugation. Could that be it? Okay, I just like.
Yeah, maybe I can make a comment. So if one looks at Goldman's paper, so of course we presented it for SLNC and UN, perfect. But if one looks at
GLN, not SLN.
Well, GLN,
SLN
yeah.
you need to modify.
Yeah,
that's why
right. Okay. No, I agree. But that was not my point. My point was that if you go through the classical groups, you will see in Goldman paper that the Poisson bracket on the loops changes.
That's right.
And so I just wanted to make a little commercial for some work that I did with Nikolai Resetikin many years ago, where we replaced G of sigma with something.
We'll come back to your work in the second hour.
Yeah, but by chord diagrams. I see. Okay, but by chord diagrams on the surface, and then that serves as a kind of universal moduli space because that works for any Lie group. And it's still subjective, and one can say a lot about the kernel this way. And, it's kind of a fun thing.
Maybe you comment during the second hour because I will get back to it, but maybe not in that detail that you mentioned now. That would be very helpful if you could.
And there is a really fun thing where the 4T relation kind of really comes out of the framework in that case. So it's not put in by hand, but it kind of forced by the fact that you want a well-defined universal Poisson algebra on chord diagrams on the surface.
Thanks a lot.
Okay, let's.